All right, good morning. Time to get started. Hope everybody's well today. Basically, just last week in our class, we kind of continued with the main phases of the hydroplate theory, kind of an overview I was doing, because I wanted to give you kind of a brief description of what happens during the theory. And as we look back, I think we'll see that so many things that are advocated in the theory are supported by science. So last week we talked about the third phase of the hydroplate theory called the continental drift phase. And this would be the phase where the mid-oceanic ridges start to rise and the plates start to slide away from each other. And basically at the end of that phase, there's a compression event where mountains are pushed up because these plates running into resistance, and kind of explains a lot of real interesting things like folded strata layers that are perfect. I mean, I'll show you pictures of this later on when we cover that. But and then we'll also see that sea life or fossils of sea life, like seashells, are found on the top of the highest mountains worldwide. It's like, this kind of fits really. If those mountains were pushed up out of the waters, as the waters then receded back into the basins, that's what you'd kind of expect. So again, we see a lot of these formations of these unusual features that evolutionary processes really can't explain. I mean, there's just no explanation for them. The imbalance in the Earth also would lead to a roll of the Earth's axis. And we'll go over that a little later on as well. But it starts to answer a lot of questions like, why do we find tropical plants and animals that live in tropical climates in polar regions? Buried under ice, like under Antarctica, for example. It's like they shouldn't be there, And we briefly discovered the recovery phase, which is the phase that actually was right after the compression event, which actually we are continuing in even to today. And during that event, we see lots of things happening. We see ocean trenches forming, and the Earth's molten core would grow because of all the motion and movement in the mantle. And sinking mountains into the mantle would cause sea levels to rise, cutting off bridges between the continents today. And we'll see that when we look at pictures of the ocean floor. This gave the ability for the animals coming off the ark and humans to repopulate across the whole Earth as God commanded them to. Eventually, as sea levels got higher over the centuries after the flood, sea level would have risen. Now the continents are no longer connected. So last week we started back at the beginning again of the rupture phase. So now I want to go through each of these phases in more depth. We have this week, next week is we won't have class next week because they're having a combo service. And then we'll have 1 week after that. So I know I won't finish all this. So we'll come back in January. I'm going to take my 3-month break as I normally do because this takes too much time to prepare. But we'll continue on. That's my plan, is to continue in January. So we got to this, we're talking about the rupture phase. We started to look in detail a little bit about some of the details of supercritical water, and just to understand how much energy was contained in the subterranean chambers, and the reason why it literally explodes out when the crack starts. And so when we look at water, we look how it's heated and just how much energy would be released. We previously discussed this water getting to a state where it's called supercritical water, which is a known state of water. It happens when water is above 705 degrees Fahrenheit and at a pressure higher than 3,200 psi, or pounds per square inch. So if you put water under a lot of pressure, we'll talk about that a little bit. You can compress water a little bit. It has to have no place for it to go, but if it's tremendous amount of weight on it, you actually compress water a little bit. So we're all familiar with water when it boils, right? So boiling is the process where liquid will transform into gas. It's that temperature where the liquid becomes a gas vapor when it's heated to a boiling point, and these gas now is released as bubbles in boiling water. So boiling is a physical change, it's not a chemical one. It means the molecules are the same, it's just they're in a different state. They're now becoming vapor rather than liquid. So boiling water will remain at the same temperature, which is pretty interesting. It'll remain at 212 degrees at sea level as long as the pressure is allowed to remain constant. So if we add more heat to the water, if the cap is off, it'll stay at 212 degrees because the release of heat above will not allow the water to actually get any hotter than that. So if you apply more heat, it simply boils more rapidly, but the water temperature doesn't change as long as the vapor produced, is allowed to escape, as we see this here in an open container. But if we place a cap on this now, so this is where it's going to change, you place a cap on the container. So now both the pressure and the temperature will now increase. And since all the mass within the container now is trapped, the density of the vapor increases. In other words, more and more vapor. The density of the liquid then decreases, and when those two reach equilibrium, or an equal amount of gas and vapor, that's the point where water becomes supercritical. So microscopic liquid drops now are suspended in the midst of dense high-energy gas vapors, and the liquid density thus equals the density of the gas. And the point to realize here that this energy stored in this is tremendous. There's just unbelievable amount of energy in this. So when you then release that, and the temperature suddenly drops and the pressure suddenly goes away, basically it's an explosion. And that's exactly what happens when the waters at a great deep burst forth, when a crack happens in the crust. So you would expect that, right? So worldwide, these subterranean chambers would all become supercritical, and then a crack forms. The crack races around the Earth. We talked about that in previous weeks, why that would happen. But this energy release would be unbelievable. I mean, it would be, nothing like we could even imagine. So I kind of think that God's angry, right? I mean, previous to the flood, he's saying he's angry. He's basically regrets having made humans, and then he was going to destroy them because of their evil. So, but again, if you probably have encountered taking the cap off of a boiling radiator in a car, you know that the water will explode out of it. I've had that experience a few times. Basically when something becomes extremely overheated like that, it's trapped, you take the cap off. This is basically a release of energy that's pretty amazing. I also have a personal experience of just how much energy can be in hot water. As my wife will attest, I drink a lot of iced tea, and I make it by putting a cup of water into a microwave, and then I microwave it for about 3.5 minutes or so, and the water's brought to a boil at that point. If you leave it in a little bit longer than you should, what'll end up happening is the water will actually explode up out of the cup. I don't know if you've ever experienced that or not, but I have a few times. All of a sudden you hear this pop, you look in your microwave, and all of a sudden the water is all over the inside of the microwave, much to my wife's dismay. And so I've had that happen a few times. But if you also take the water out and before it reaches that point, one time I took a group of tea bags and I just set the cup down on the counter and I just popped the tea bags into the cup, and the water just burst out. It was just exploded out, and it was all over my hand. It went all over the counter. It burned my hand. I was just shocked. I had no idea. So I'm much more careful now. But boy, my hand was burnt for a couple of days. It was terrible. So now I know just how much energy there can be in water. And this is just boiling water at 212 degrees, not 705 degrees under much higher pressure. So that was some information about supercritical water and how much energy it has. But another form of energy is stored in supercritical water, and it's called ionization energy. So I want to just briefly go over that. In order to understand that, you really have to understand a little bit about atomic structure and know what ionization is. So basically, it's the process where a neutral atom or molecule gains or loses electrons, becoming electrically charged. And the electric charges are called ions. And so here we see a representation of an atom, and I'll get my pointer going here. Here's an atom, And what we see here is that they're made up of little particles. There's three types of particles. There's neutrons, protons, and electrons. And each atom's nucleus, or in the center, as we see here, contains the neutrons and protons in an atom. And the protons are the positively charged, and neutrons have no electrical charge. And then around that, we see electrons that orbit around the nucleus. So we'll see these in these circular paths around here. Electrons are the negatively charged particles that orbit the nucleus in specific levels or shells, depending on the atom that you're looking at. So the electrons, say there's multiple shells in many atoms. This one just really shows one with three there, but if you look at different atoms, there's about 90 or so or more different kinds of atoms that exist in nature. And for example, if you look at iron, which we know about iron, the metal iron, it has 26 protons in its nucleus, and that determines what it's called its atomic number, which is 26. And then ordinary atoms of an element also have the same number of electrons. So the iron would have 26 electrons circling around the atom. So if the outermost shell is complete or filled with the right number of electrons, the atom's what's called stable. And there's no or very little tendency to interact with any other atoms. However, it does happen that sometimes an atom will lose an electron and will become unstable. And when that happens, it's called an isotope. And one thing to kind of remember too, as we're looking at this, is that this picture on here, I'm sure you've seen something like this. This is not at all to scale. I mean, this is just a representation that we can somewhat understand. But if you can visualize this makeup of this atom, the distances between the nucleus of an atom and its electrons that orbit are much, much greater than I can show in a diagram. It would never make sense to show it the way it really is. So think about the scale of this. The atom is about 10,000 times larger than the nucleus, which basically means that most of the atom is actually empty space. That's why they can be compressed a little bit, but most of it's empty space. So think about a large sports stadium. You've probably all been to a football game or been to a large stadium. And now imagine on the 50-yard line, right in the middle of the stadium, you put a marble, just a regular marble. Okay? That would be the nucleus of the atom. And the electrons will be flying around that nucleus roughly on the outer shell of the stadium. That's how big it is. I mean, that's how, and then the electrons are just a speck. I mean, they're tiny. They're just tiny, tiny. So this gives you some kind of an idea. So I think about this, man, that's amazing. It really is incredible when you think about this. Did this all happen by random chance? I mean, how did this come to be? I mean, what made this? And so you start thinking about it. I'm thinking there's a brilliant intelligence behind this. You know, in order for this ever to occur, there had to be something that would set up these physical properties that allow this to happen. And I think, you know, if you look into Scripture, Colossians 1:17 tells us something that I think is profound here. It says that Jesus himself is a sustaining power over the entire universe. And I'm thinking that's even the smallest particle of atoms. So Colossians 1:16, the previous verse, says that all things were created in him and by him. Verse 17 then emphasizes that they all hold together through him. I mean, I think, we don't understand these nuclear forces that hold atoms together. We don't understand gravity. We don't understand how orbits work. We can observe it, right? We can see it happening. We just don't know why. We have no idea why. So he maintains the order in the universe, the structure of everything, I think from the smallest particles to the vastest galaxies. And without his ongoing power, I think all things will fall apart. I think this is really, truly profound and truly amazing. So when we talk about the hope we have in Christ, to me, it's like, it's not even a hope anymore. It's a certainty. I mean, when you see this and everything else and all this leads to one conclusion, and only one possible way this could all happen. To me, it's a certainty. So now when we look at atoms, when a group of two or more atoms are held together by chemical bonds, they form what's called a molecule. And atoms, which are the basic building blocks of elements, join together to form molecules, and they create larger structures. So example, here's a water molecule. Here's something everybody's familiar with this, right? You know what a water molecule is, right? It's made up of one oxygen atom and two hydrogen atoms, unless it's labeled H2O. You'll encounter this probably almost daily. And this indicates that it has two atoms of hydrogen and one atom of oxygen. Again, you almost think about how amazing even just this is, because hydrogen and oxygen are gases. They combine together to form a liquid. You know, how does this happen, right? I mean, it's like mysterious. And to me, there's a design behind all of this. Where there's design, there's a designer, right? It just makes sense. So with that background, I want to look at ionization now. So this, again, is another source of energy in those subterranean waters. So this diagram represents molecules of water under normal conditions in an open environment. In other words, no lid on the top of our pot here. They move around in the liquid at a rather slow pace. They'll increase pace as the temperature rises, and they'll decrease this movement or pace as the temperature goes down. But here's, normal states. They're not moving around all that fast. So what ends up happening is, collisions are rare. We'll see occasionally molecules of a fluid, such as water, will collide together. And when they collide with enough energy together, what'll end up happening is they'll start breaking out these electrons from the atoms, creating ions. So we see here as an electron, which is our negatively charged red circle there with a negative sign in it, has broken free as a result of a collision. But this happens pretty rarely in an open environment. It doesn't happen all that often. However, what happens if we close the lid on our container again and we increase the pressure enclosed in this container? Now, this would have been the case when there was 60 miles of rock, basically crust, above trapped waters, trapped that below the surface, creating tremendous pressure. So here's the pressure we're talking about. And a closed, pressurized environment forces these molecules to be closer together and increases the fluid pressure and makes these collisions much more likely. And now if you add heat, what would you think would happen now? Okay, they're going to start moving even faster, right? Now they're really whipping around here, right? And now what would you expect to happen? More collisions, right? And more proximity, increased movement causes more collisions, creating more ions. And this causes the ionization of water. So now think about this. What would happen if the container is suddenly opened? Think about now, we've got all this energy trapped in a container. All of a sudden we release it. If the pressure suddenly drops, which is what would happen when this pressurized container suddenly opened up, they would add to the explosion of the fountains of the Great Deep when that was opened up. So we have, the explosion of the water anyway from supercritical water when it suddenly has a tremendous pressure drop. We have potential energy of the weight of the crust above the waters, and then we have kinetic energy, which is basically the energy of the motion. Kinetic energy is energy of something in motion, pressing down. That's why there's an explosion. That's why the fountains of the Great Deep burst forth. And involved in that too is nuclear energy, which I don't want to sidetrack on that now because we'll get very sidetracked. I don't want to mess with that right now. But this would have been, again, a tremendous release of energy as these molecules explode. This would release much heat into the fluid. And then, again, as we talked earlier, twice a day, because of the tidal pull of the moon on the Earth, it would have lifted and then released the crust, which would have caused a lot of movement in the waters below with a lot of heat. Would be this heat built up, which is where we would get it to be supercritical. Yes?
Just in a previous lesson of yours, you said that the water was different than the water we have on the surface.
Well, only in the fact that the water itself is the same. it's the same water. It just becomes supercritical, it becomes in a forced state of water.
I thought you said it had more of something.
Well, it had more ions in it. Maybe that was what I said.
Maybe that was
Yeah, I don't recall, but yeah, but water, it's H2O. It's the same water below and above, combines later after the flood, and then, that's where the waters come from that can cover the entire surface of the earth. Essentially. So this became very ionized and supercritical, and again adds to the explosion.
We just found out that they found a water sample that dates back farther than any sediment sample on Earth. So what proves the water?
Well, yeah, the other thing we'll get to later in the class too is that there is deep water in pockets far deeper below the surface than it ever should be. And we're finding pools of hot, salty water, saline water, trapped below mountains. We can seismically determine this by sending waves. We can't go down that far, but water on the surface cannot seep below about 5 miles from the surface down. And the reason for that is that there's so much pressure, it seals off any cracks so that the water couldn't seep down any further than that. But they've done digs where they dig down the surface, from the surface. They'll go down 7-8 miles now and they'll find hot, salty water. Or we have seen, under the Tibetan mountains, we'll talk about this later, but we'll find pools of pockets of water, hot water, well below that. 30, 40, 50 miles down, where it shouldn't be. It shouldn't be there. There's no way it should have been able to get there. So.
When you're talking about what happens to the water when it's enclosed, I'm trying to relate that to the flood because I'm thinking of all this open water. But is the closed idea the water under the earth? Is that what?
Yeah, well, the water is like this diagram is going to show you. We had pre-flood water trapped below a crust, okay, which was created that way. I think Genesis 1, verse 6 through 8 tells us this, and it develops this arrangement of surface water, a rakia, or basically a separation of the surface waters from waters below, and we have trapped water well under the crust. And there's reasons for that I won't get into now because I don't get too sidetracked here, but that's where this water is, this water below, which then when the rupture occurs in the crust, when the flood starts, that's released. And that's what we're talking about now, is when there's this release, there's this explosion because of all this heat buildup and pressure and that's in this trapped subterranean water chambers. So here's again side view of the pre-flood conditions, and it would be this way from just after creation up to, for centuries, up until the beginning when the flood occurs, when the flood starts. And so the trapped waters, below here get to this point where they're supercritical. We see now that the pillars, that touch where this crust is sagged down, now allows surface waters to drain into the depressions, which we see in Genesis 1, 8 through 10, where the land rises out of the waters when land forms. Doing the calculations that Dr. Brown has done, he knows that this temperature below here would have been, and the pressures would have been well more than enough to get this water to be this supercritical. And the water also, there's another aspect of this too, is that under so much pressure, we can see that actually water will compress a bit. It doesn't seem like it would because we don't really run into that ourselves, but molecules of water are already somewhat close together. So there's not a lot of room for them to be compressed. So think of a gas. Now we can compress gas, right? We can compress vapor gas, like we have propane in our propane tanks. We've compressed that. But water is much less compressible than a gas, but it is still somewhat compressible. So today, you think about the ocean. Most of our ocean is about 2 to 2.5 miles deep. And so if you measure the volume that water takes up that deep, it actually is about 1.8% smaller. It's about 2% smaller because of all the pressure on that water. It causes the volume, the size of a particular amount of water to actually be compressed somewhat. And so again, adds to this explosion. So when the pressure again is suddenly released, the water will expand back. It's not a lot, but I mean, it would add to it, right? Add to that explosion. And so we also studied earlier that these supercritical fluids are used today. And one of the things they're used for is there's a great potential for them to dissolve minerals. We talked about this a couple weeks ago. We also know that water is a good dissolvent, right? Water, just regular water. We put our dirty dishes in the sink and put water in there, and it helps to break things free and dissolve things, right? So that's what's going on here, I think, in the deep here, is that as we look into a small section of the crust now, we're going to just kind of zoom in on this now, a small portion of the underside of the crust, this aspect of the supercritical water would have begun to dissolve the chamber ceiling. In other words, the ceiling of the chamber above would have started to dissolve some of the minerals. It would also start to do that to the floor as well. So for centuries, this supercritical water would have dissolved many of the minerals in the granite-like quartz, which would produce limestone and salt and magnesium, and also would dissolve below the mantle. And so it would create these porous openings, as you'll see kind of in the rock there. And these eventually precipitated out into the chamber and would have blanketed the chamber floor with a lot of sediments, a lot of material that was dissolved by the supercritical water. And so we now see that there would be a source of these sediments that we rush to the surface when the fountains open up. You know, when the fountains are great deep, a lot of this is going to get pushed back out, you know, and becomes our sedimentary layers, which again we'll talk about when we get to that part. But the porous part of the region of the mantle that was dissolved by supercritical water is now known. It's called the Moho. And the Moho basically is measured today worldwide. It's an anomaly that regular science can't figure out. If you do seismic readings of the Earth, they see that there's a dent in the crust, and then they get to the Moho, which is this strip, which was where the waters were, you know, until they were pushed out. There's still a lot of sediments in there, so it's not the same consistency that the rock above is and the rock below is. And you'll see this, I'll show a slide in future classes here that'll show the Moho at different varying depths, but worldwide. It's like, okay, well, how do you explain that? I mean, this perfectly explains where this Moho comes from. You know, how did it get there? And now here's a section of the ocean floor today that's pushed up, and this is where the mid-oceanic ridges will start. And we'll show you that again a little bit later as well. But that causes them to push up, and we see today plumes of hot supercritical water still coming out, known as thermal vents or black smokers. They're still escaping from the porous Moho beneath the ocean floors in places. So again, it all fits together. So we want to look now at the processes of force balances that would have occurred in the crust and the mantle. So due again to the tremendous weight above the mantle, there would have been tremendous pressure on the crust below, as these blue arrows represent. So here's the weight of all this pushing down. And so the very famous scientist, I think everybody knows, who Sir Isaac Newton was, he developed something called his third law of motion. And the third law of motion states that for every action, there is an equal and opposite reaction. This is a fundamental law that we all are aware of pretty much on a daily basis. So a classic example of this is a baseball example. So if a batter exerts a force on a ball with a bat, when he swings a bat and hits the ball, there's an equal and opposite force back on the bat and also on the ball. So the ball's coming toward the hitter, the batter hits it, all of a sudden the ball goes the other direction, right? So this is the reaction on the ball. This is what happens to the ball. The bat itself has a reaction to the force also. It causes a vibration of the bat. And that would be felt by the hitter in his hands and wrists too. or in some cases, there's enough force that it actually breaks the bat, right? You've seen that probably happen in baseball games. So this is the fundamental principle of physics that stated when one object exerts a force, this is the action, in this case, the granite crust above, on a second object, in our case now, is the crust or the mantle below, the second object exerts an equal and opposite force, which is the reaction. And these always occur in pairs. I mean, there's always an action-reaction kind of a force. So this tremendous weight actually will compress the rock underneath, which will then expand back out later when all this weight is taken off. So there's compressibility in the rock down here. But this is basically, you know, a very well-known law of motion by Isaac Newton here. So this is the red arrows now represent the reaction force from the mantle pushing back. So as we progress here, pay attention now to the blue and red arrows and what happens here. So if now a crack occurs in the crust, and this is our fountains of the great deep bursting forth. So at the location of the crack, what ends up happening? All of a sudden there's a sudden pressure drop, the downward pressure of what was below that location. So keep that imbalance in mind as we follow what would happen next. When the crack opens up, the pressure in the middle of the granite plate, far away from the rupture, would still be high pressure. It's indicated by the red lettering here, where it says high pressure. So away from the crack, there's still a lot of pressure on that. As we now get closer to the crack, we would have areas of low pressure, shown here in the yellow lettering. So we see the high pressure away from the crack, low pressure. As this opens up, the pressure all of a sudden drops. This would cause the edges of the unsupported granite now to bend down. Remember, there's some flexibility in this because of the size, and it's just huge. So now we've got some flexing in this crust. It now allows it to bend down, creating what would be thought of as a nozzle or a tapered nozzle at this crack. So at the nozzle, there's a separation between the plate above and the mantle below, and it would have been smaller than that when it was further away from the rupture. So here we see this tapered nozzle. So as the pressure dropped in the subterranean water, the pillars in contact, and this is where the pillar is where the crust above touches the mantle below, would have increased pressure there. We'll see those arrows now. We'd have more pressure there. We'd have increased loading where the mantle and the crust touch. Eventually, the pillars, which were brittle and porous, from centuries of contact with this supercritical water, would have failed, and the weight would have started now to break the materials of the pillars into fragments. So if you see the breakup here in the pillars, this would have also caused great earthquakes to happen. So we'll see with our little animation there. This would have caused a lot of things to happen in that crust, again, that we'll talk about later. We talk about the origins of radioactivity, but this would have said basically electrical charges through the crust, creating radioactive elements in the wake of that. So this explains where radioactive elements. This is a known process too. This is not something that's, you know, unknown. This is something that would have happened. So again, we talked about there wouldn't have been radioactive materials in a good creation because that's harmful to humans at the end of the creation week. So here we see, I think, a valid scientific and biblical reason for where radioactive materials come from. So water escapes from the plate, and as that happens, they would have bent down and causing this nozzle-like condition at this location. Every time the hydroplate oscillated down, it would have partially closed this nodule-shaped edge of the plate, and now we have basically an entire ocean of escaping water. It's forced to slow down and suddenly stop. So when the plate comes in contact at the nozzle with the mantle below, all of a sudden it cuts the water off. And this produces something called a water hammer. Now you may be somewhat familiar, or maybe encountered a water hammer yourself. So a water hammer is basically like a loud banging noise and a pressure shock wave that happens or occurs when flowing water is abruptly stopped or forced to change direction. So you may have heard this like when you shut off a hose, let's say, or a valve real quickly, and all of a sudden the pipes will make a bang sound and they'll vibrate. That's called a water hammer. This is something that will, can sometimes break or damage pipes and fittings. This is because water hammers cause pressure spikes that are many times the initial pressure of the flowing fluid for a split second. And then the same thing would have happened now in the subterranean chambers as the hydroplates oscillated down, closing this valve or opening it rapidly. So every time this happened, velocities at the crack would have spiked as well. In other words, velocity of the water coming out would have spiked. We would have had, huge amount of pressure coming out, and it would have been cut off for a little bit and would come back. So the vibration and flow under the plate would also produce what's called flutter. And flutter means to move back and forth rapidly. Most people are familiar with the fluttering of a flag, right? So a good illustration of that is a flag in a fast wind. So a flag flutters in a fast wind due to what's called aerostatic elasticity or instability. So this is a complex interaction between the wind and the flag's structural properties. And so when the wind flows over the flag, it creates pressure differences, causing forces and bending of the flag. And this produces an oscillation known as flutter. So this is a phenomenon that's studied in physics and fluid dynamics. And the same principles would have been present in the crust, which is basically the flag in our example. So think of the crust as our flag. And it would have flapped a little bit. So as the crust comes down and spikes, it creates flutter or movement in this crust. And this is important when we're going to look at how these sedimentary layers form. We'll see huge amounts of sediments on the surface, tremendous amount of movement in the waters because of all the motion of this crust, and that rapidly allows sediments to form in different layers, something called liquefaction. I'm getting a little ahead of myself here, but we're going to come back to that. But this is the reason why we see these sedimentary layers form so rapidly. Evolutionists, of course, tell you, it takes millions of years for this to happen. It doesn't. And we can demonstrate this easily, experimentally. And also, we see an example of this happening when Mount St. Helens exploded. There actually were sedimentary layers rapidly formed when that happened. So again, keep that in mind as we move forward. So then the flutter produces the conditions where the crust rises and lowers, makes contact with the edge of the mantle. As we just talked about, it would produce the phenomenon known as the water hammers. And so the flutter produces these water hammers. And then whenever a fluid passes over an unsupported plate, again, it produces this flutter. Now the plates, again, were 60 miles thick, of course, but that's relatively thin compared to the immense scale and size of these plates. So now I want you to watch carefully as I start an animation of this. It's kind of slow. You kind of want to look carefully. But what you'll see basically is you'll see the pillar, which is now raised up off the floor. It will come down because there's so much motion and movement that's happening in this subterranean chambers. It'll actually lift the pillars up off the floor, and then they'll come back down and touch the mantle again. When that happens, you'll see that this crust on the nozzle will go up and come back down again and slam on the floor, and then you'll see spikes of liquid coming out of here. So just kind of watch this as this goes on. So that's kind of slow. You got to watch it carefully. But here we see the pillar hitting the floor of the mantle. We see now huge amounts of water being pushed up through the crack. We now see broken segments, these little black things here, would have now lifted up and now been shot because of so much force up into the atmosphere. And actually with so much force, it will send things out beyond Earth's atmosphere. So this becomes the source, and we'll talk about this probably next week or 2 weeks from today. This becomes what are going to form into comets and asteroids, what hits the moon to produce the craters on the moon. Okay, because there's no explanation, reasonable explanation as to why the moon looks the way it does. it's been shot from one direction. I mean, it's been shot, impacted very hard from one direction on the face that we see. The moon always faces us, you know, it doesn't rotate. We always see the side of the moon that faces the Earth. And there's a other side of the moon too. It's totally different. So we'll get into that when we get into talking about the moon. But so hydroplate theory again proposes that during the beginning stages of the flood, this supercritical water rockets out from under the plates, and then this induced flutter in the plates. This lasted probably several weeks or maybe a few months. And then return oscillations lifted the fractured pillars from the base and then slammed them back down on the mantle. This produced more fragments that were then swept up and up. So again, it's kind of hard to imagine 60-mile thick crust bending, but if you consider that the area of these plates were thousands of square miles or so across a continental scale, then it becomes not so hard to understand this, to see this. So many of the views here you see are not to scale, of course. I have to do it this way, so to speak, to give you some kind of idea what's going on. But if you take a look at North America, for example, you're familiar with the United States. This is, of course, not how it looks before the flood. This is post-flood. But just to give you some kind of an idea, you have a crust. Let's say the United States is about 2,500 miles across, and the crust is 60 miles thick. It's not hard to start imagining that there would be some bending or flexibility in this crust over that size now. So to give you a little bit of perspective, the Earth is 7,926.2 miles in diameter. You should remember that, right? Just in case you need it. But the crust is only about 60 miles thick. So it comes out to be about 7/10 of 1% of the diameter of the Earth. The total diameter of the Earth, only about 7/10 of 1% is this crust. So to put that in some perspective, think of an onion skin. So if you look at an onion skin, it's many times thinner than the rest of the onion bulb, right? Its thickness is extremely thin. So when you take that off, of course, the edible part of the onion is underneath that, maybe a few inches in diameter, right? But your skin is extremely thin. So the proportion of an onion skin to the onion is kind of similar to this. It's kind of similar to the proportions of what the Earth's crust would have been compared to the diameter of the Earth itself. So next time you prepare a salad, if you eat onions, and I don't, but just think of this, right? Okay, think of the fountains of the Great Deep and think about the crust here when next time you cut an onion. So again, it's not too difficult to imagine bending or flutter in the crust at that point. So at the point of the crack, the pressure drops from around, Dr. Brown is estimating now that the actual pressure would have been about 372,000 pounds per square inch, not 3,200. So it would have been even higher than that due to water hammers. But now it drops to near atmospheric, normal pressure conditions. So what ends up happening is there's an explosion. This expands the gas, increasing its volume by 1,600 times. This phase changes the supercritical water and tremendous amount of energies. And what happens? Boom. There's an explosion here. And this is a good place to stop. But that's what happens, I believe, when the fountains of the Great Deep burst forth. Thank you. We'll see you 2 weeks from today.